In the early days of an application, scaling is simple. When your database gets slow, you give it more CPU, more RAM, and faster storage. This is vertical scaling, or scaling up. It is the most straightforward path because your application logic remains unchanged. However, every physical machine has a ceiling. Eventually, you cannot buy a bigger server, or the cost of the next tier becomes exponential. This is where big data, not as a buzzword, but as a technical reality, breaks your schema. When a single primary instance can no longer handle the right throughput or the sheer volume of disk I/O, we must look toward horizontal scaling. We need to move from one giant machine to a cluster of smaller ones. This brings us to the complex but powerful world of database sharding. Sharding is the process of breaking up a large logical dataset into smaller, more manageable pieces called shards. Unlike partitioning, which often happens within a single database instance, sharding implies that these pieces are distributed across entirely different physical machines. Imagine a users table with 100 million rows. In a sharded architecture, we might put users 1 through 50 million on server A and 51 through 100 million on server B. Each shard is its own independent database. They don't share memory or disk. This shared nothing architecture allows for massive parallelization of writes, which is usually the primary bottleneck that sharding aims to solve. But this separation comes at a steep price. Your data is no longer in one place. The most critical decision in sharding is choosing your shard key. This is the column that determines which shard a specific row belongs to. If you choose user ID as your shard key, all data for a specific user will live on the same shard. This is ideal for multi-tenant applications. A good shard key must satisfy two conditions: high cardinality and even distribution. Cardinality means there are many unique values. If you shard by country and 90% of your users are from the US, one shard will be overloaded while others sit idle. This is known as a hot shard. A poor shard key choice can actually make your performance worse than a single server because it creates localized bottlenecks that are difficult to resolve without migrating massive amounts of data. There are two primary strategies for mapping keys to shards: range-based and hash-based. Range sharding maps continuous ranges of values to specific shards. For example, user IDs 1 to 1000 go to shard 1. This makes range queries, like give me all users created in October, very efficient if the key is a timestamp. Hash sharding, on the other hand, applies a mathematical hash function to the shard key. The result of the hash determines the shard. This is excellent for ensuring data is spread evenly across the cluster, preventing hotspots. However, it makes range queries nearly impossible, as sequential IDs will be scattered randomly across every server in your fleet. You trade query flexibility for better load balance. Once your data is split, your application can no longer simply connect to the database. You need a routing layer. This is often a proxy or a smart client library that knows the sharding topology. When the application sends a query, the router inspects the shard key in the SQL statement. If you query select name from users where ID equals 42, the router hashes 42, finds that it belongs to shard 3, and forwards the request only to that machine. This keeps the system fast. But what happens if you query a column that isn't the shard key? The router has no choice but to perform a scatter-gather operation, sending the query to every single shard and merging the results. This is the performance killer of sharded systems. The biggest technical hurdle of sharding is the loss of relational features. Standard SQL joins across shards are extremely difficult and usually unsupported. If your orders are on shard A, but your products are on shard B, a join requires moving massive amounts of data over the network to a central spot to merge them. Similarly, ACID transactions become distributed transactions. Ensuring that an update succeeds on two different shards simultaneously requires protocols like two-phase commit, which are notoriously slow and prone to failure. Most sharded architectures force you to denormalize your data, copying information so it's local to the shard, or to handle consistency at the application level. You are trading database-level guarantees for planetary scale throughput. Operations also become significantly harder. What happens when your shards are full? You need to add more shards.
a process called resharding. This involves moving existing data from the old nodes to the new ones while the application is still running. It is a high wire act. If you use simple modulo hashing, adding one server changes the destination for almost every key, requiring a total data migration. To solve this, engineers use consistent hashing, or virtual buckets. These techniques ensure that when a shard is added, only a small fraction of the data needs to move. Even so, the operational overhead of managing 50 databases instead of one is a massive burden on any engineering team. Monitoring, backups, and schema migrations all become n times more complex. Because of this complexity, the first rule of sharding is don't shard until you absolutely have to. Before you partition your database, ensure you have optimized your indexes, implemented read replicas, and perhaps introduced a caching layer like Redis. Sharding is a one-way door. Once your data is distributed, it is incredibly difficult to go back to a single instance. It is the nuclear option of database scaling. Use it when your write volume exceeds the capacity of the largest possible machine, or when regulatory requirements, like data residency, force you to keep certain users' data in specific geographic regions. Sharding is a tool for billion-user problems, not thousand-user problems. Build for the scale you have, but keep your schema flexible enough for the scale you want.